All right, as promised, I wanted to finish up today's lecture slides, going over them so that you'd have them to study for the assessment on Tuesday. So here we go. So I know I already did this, but I am going to go through this particular problem one more time just so you can have access to it on a video. So remember we had two masses connected by a string. One's on a table and the other one's hanging free. In this case, we actually have friction, and then we're asked in an indirect way to find the acceleration of the objects and then also the tension in the string. So I wanted to go through how we would do that. So the first thing I'm going to do is I'm going to label the forces for each mass. So I have the normal force for mass 1, its weight. I have the friction because I'm already told that everything is accelerating to the right and then of course down. And then we have the tension in the rope. So that's mass 1 forces. Mass 2 forces have the same tension in the rope, but it pulls up on mass 2, and then the weight hanging down, m2g. Now I'm going to apply Newton's laws for each of these masses. I'll start with mass 1. Now, I'm going to look at the forces in the y direction first, and you might think that we don't need to because nothing's really happening, but we're going to need the normal force to calculate the frictional force that's acting on that mass. So in the y direction, I have normal force acting up and its weight acting down. The object is not moving up and down in the y direction, so those two forces add up to be 0. So I know that the normal force for mass 1 is just equal to its weight. In the x direction, this is the way that it's actually accelerating. I have tension and friction. Those two forces are opposite each other. I'm saying to the right is positive, to the left is negative. And so the acceleration is also to the right, so that's going to be positive as well. So see, I put the two forces on the left-hand side and m1 times a on the right-hand side. I'm going to do a little bit of substitution for the frictional force because I know that it's defined as the coefficient of kinetic friction times the normal force, but I already found the normal force, so I'm going to substitute that in for it. So I'm left with this equation. This is one of my two algebraic equations that I'm going to be manipulating to solve this problem. The other equation will come when I look at mass 2 and evaluate it according to Newton's laws. For mass 2, I have tension acting up and its weight acting down. Those are the only two forces I have. It's accelerating down, so that's in the negative direction. So I'll make that equal to minus m2a. Down is negative. The acceleration is negative. It's in the same direction as the force of gravity. So here's my two equations. Now, how I solve them, there's probably quite a few different ways I could go about doing this. I'm going to show you what I would do. You might do it differently. It doesn't really matter as long as we're both careful and don't make any little silly mistakes. I'm going to solve for tension out of this equation. So I'm going to say tension is equal to m2g minus m2a. Then I'm going to take this and I'm going to substitute it into this equation. And that'll give me m2g minus m2a minus mu k m1g equals m1a. So I'm just going to get all my expressions that involve acceleration on one side and everything else on the other side. And so I come up with an expression for the acceleration. This is when I would plug in the values for these numbers. And so I would, if I put in the values for the masses and coefficient of friction, I get an acceleration of 1.105 meters per second squared. So that's my acceleration. Now, they actually didn't ask me to find the acceleration, but I have to. I need to know that. But they're going to help, that's going to help me find this answer to this question. If the blocks are released from rest, how fast are they moving after they go 3 centimeters? That's a one-dimensional motion type of problem. So if they start from rest, I want to know the final speed. I would use this. And 3 centimeters is 0.03 meters. And I would find a velocity. This is where I said in class my acceleration was kind of small, so my velocity ends up being very small. But it is just 2 blocks. I could also use this value for tension and put it into any of these equations. And solve for the tension. I don't have that number off the top of my head, but that's how I would do that problem. So that was the first problem I did go over in class, but I just wanted to quickly go through it in case you wanted a video recap. All right, so now we get into some questions. Here we're told a box on a rough surface is pulled by a horizontal rope with tension T, and we're told the box isn't moving. Well, because we have a rough surface, we know that there's also a frictional force. And because it's not moving, it has to be static friction. If it's not moving, some of these forces in the x direction have to add up to be 0. So tension minus the force of static friction adds up to 0. And so those 2 forces are equal. If the opposite was true, you can't let the force of static friction get bigger than the tension, because that would imply that the object moved to the left. That's one of the reasons why we say that the force of static friction can have a lot of different values, because it just adjusts to be as big as it needs to be. Okay, so then here's a problem. This is really similar. We've had a very similar problem posed to us a couple times, and I've talked about it. I'm comparing this to the lawnmower problem because we're saying the box is being pulled to the right over a rough surface, so there is friction. This time it's going to be kinetic friction, and we're told that T is greater than that force of kinetic friction, so it's speeding up, so we do have acceleration in this direction. And then we're told the rope breaks, and we want to know what happens. When the rope breaks, we go from this picture to just a box with some friction acting against it. And so now my acceleration is going to be to the left in the same direction as the frictional force. So what that's going to do is it's going to slow down the box in a steady rate, because this is going to be a constant value, this acceleration. And so the only answer that makes sense is for the box to slow steadily until it comes to a stop. All right, here is kind of practicing how do we find the direction of the force acting on the crate. So right now, if my crate is on the incline and you want to know what the friction is. So think about what the forces would be that would be acting on this object. For one, I have the normal force and I have the weight. Now, this weight breaks down into 2 components, a y component and an x component. The x component of the weight, right here, tends to pull the box down the incline. And so without friction, we know this box would just slide down the slope. So that means that the frictional force has to be opposite to the weight in order to keep it on the incline. And so the frictional force will point up the incline. Now, in the next case, we change it slightly because now we have someone pushing it. The physicist is pushing weight up the crate up the incline. We still have the normal force, and we still have the force of the weight. So it still has a force of its weight tends to pull it down the incline, but the physicist is pushing hard enough with his force up the incline to make it move. And so we have to consider the fact that friction is going to oppose the motion. And so this means that my frictional force has to be down the incline in this case. All right, now let's think about how we walk. And I think I've talked about this a little bit in class. The idea that when you're walking, you have to get some sort of force moving forward in order to kind of let you move forward. And so we think about where our feet are interacting with the floor. And now they're talking about it as being friction. Now, if it's kinetic friction, then our shoes would be slipping. But if we have static friction, we don't slip. And so you think about, as you walk around during the course of the day, do you want to slip? Do you want your feet slipping against the floor, or do you not want them to slip? And I'd say we do not want to slip. And so anything that has kinetic friction, we would say no. Now we have to look at the question more closely. It's asking what would be included in a free body diagram for your body. Well, that means it has to be a force acting on you. And that's why it would not be the force that your shoes exert on the floor, because that wouldn't go on your free body diagram. And so by process of elimination, but also because it makes sense, we choose answer B. Now we get to this, I think this might be the final question. I'm not 100% sure. But this problem where we have someone pushing the crate and we have two different coefficients of friction, the coefficient of static friction and the coefficient of kinetic friction. And so basically we're being asked to find the value of the force of friction for a bunch of different values for the push. So I think the first thing we want to do is we want to say, what is the maximum force of static friction? So the maximum force of static friction is that coefficient of static friction times the normal force. If I look at my vertical forces, I would see that my forces in my y direction are just the normal and the weight. So my normal force is equal to the weight of the crate. So I can find this maximum force of static friction to be 0.7 times the 20 kilograms times 9.8. And so that ends up to be the maximum force of static friction that I could get is actually going to be 137.2 newtons. That's pretty big. Now, what we would know is as long as P is less than this maximum force, the crate won't move. So when P is equal to 20 newtons, we would have P minus the force of static friction, because it's obviously less than 132, is equal to 0. So my force of static friction is equal to P, so it's equal to 20 newtons. And the same thing is going to happen for this one and this one. These are both forces that are less than the maximum force. So if P is equal to 30 newtons, the force of static friction is going to be 30 newtons because we're below the threshold that's going to make the crate move. And if P is equal to 120 newtons. The force of static friction, again, is 120 newtons. Again, so it's only when P is equal to 180 newtons, this is greater than 137, so it's going to move. So now we have forces in the x direction are actually going to give acceleration. And so we have P minus the force of friction equals ma. But the force of friction is going to be equal to mu, the kinetic, times the normal force, which is mu times m times g. So it's 0.6 times 20 times 9.8. And that force of friction, if I do the calculation, is 117.6 newtons. Easy peasy. So the really important thing here to notice is for friction, for static friction, it has this maximum value that it can exert, but a lot of times the force of static friction will be smaller because it only has to be as big as the force that it's trying to fight against. Oh, here was a problem I forgot about, the inclined plane problem. It's just asking us how we would express the force of friction in this case. Basically, I'm asking you because the force of friction is mu times the normal. And I want you to think about what the normal force look like for an inclined plane. So for the inclined plane, we would look at forces in the y direction first to find the normal force. And the normal force is positive, but then we have the weight, the y component of the weight. And those are the only vertical forces because of the fact that this is my y-axis in this case, just as you see right here. So the normal force is equal to W sub y, which is actually just equal to mg. And you can see that this is adjacent to the angle, so that's be cosine of 25. So this force of friction, then we could write it as mu times the normal, but this is how we write the normal. So we have mu sub k mg times a cosine of 25 degrees. This is a really good example of a situation where the normal force is not equal to the weight. Here's another question. A brick is resting on a rough incline. The friction acting on along the incline, is it less than the weight of the brick, greater than the weight of the brick, 0 or equal? Good question. Kind of, I think we saw something similar earlier. So here's the normal force. Here's mg. And here is the friction. So if it's not moving, we'd have to ask ourselves what forces would be acting in the x direction, and we definitely have the friction acting up the incline, but we have to remember that we would also have the x component of the weight would be acting down the incline, because we would break this down into a y component and an x component. And so that's x component is what we're looking for. And then remember that this angle and this angle are the same. So F, the minus mgx, would be the way we would express mgx would mg sine of theta. And so the frictional force would be equal to mg sine of theta, which would be less than mg, because the sine of theta is less than 1. And so the frictional force is less than the weight of the brick. All right, so I'm going to talk just a little quickly about how your apparent weight would change in an elevator. This is sort of a topic that comes up, and I wanted to go through it because we never really got to go through it in class. It has to do with what happens when we are in an accelerating frame of reference. And so here in the first picture, we see a guy in an elevator. What they're trying to show is that he is standing on a scale, and he's also in the elevator, and they've drawn all kinds of forces. There's the force of the weight that acts on the guy. There's the tension in the cable of the elevator. There's the normal force that the scale exerts on the guy, but there's also the force of the scale acting on him. There's the weight of the scale. There's the force that the scale exerts on the floor. There's a whole bunch of stuff going on here. And so the first thing we have to do is, like, what are the forces that we're interested in? And so the forces that act on the person are shown in the second picture. The only forces that we care about are the weight of the man, because that's the force the earth exerts on the man, and then the force of the scale that the scale is exerting on his feet. What we want to keep in mind is the force of the scale will be whatever we see that will be his apparent weight. The idea being that if he was actually doing something like standing on a scale in an elevator while it was accelerating, the scale would read how much he appears to weigh. Now, if this seems weird, I want you to think about if you've ever been on an elevator that moves really quickly, and how if it accelerates up really quickly, you might feel heavy. And if it accelerates quickly downward, you might feel kind of light. And so this is sort of a precursor to what results we're going to see. So let's suppose that the elevator accelerates upward. That'll be case one. So we're going to say our acceleration is up. The way that we would look at this is we would look at the forces acting in the y direction and set that equal to the mass times acceleration. So we have the force of the scale minus his weight, mg, is equal to ma. Because the acceleration is up, that's positive. And then if I rearrange this to find the force on the scale, I find that it's equal to mg plus ma. And so he appears to weigh more than his actual weight, because we actually see that there's a term added to the force of the scale due to the acceleration of the elevator. Now let's look at the opposite case. If we let the elevator accelerate downward, we look at our forces in the y direction. Our forces haven't changed. We have the force of the scale minus the weight. But what changes is over here on the right-hand side, because the elevator is accelerating downward, we have to give it that negative sign. And now when we solve for the scale, the force the scale exerts, we see that it's actually less than the weight. So he appears to weigh less. What's happening here, in a sense, is because the elevator itself is accelerating, when it accelerates up, it kind of pushes up into the man, and that makes him press down harder on the scale, and that's why he appears to weigh more. And then the opposite is true when it accelerates downward. The elevator's literally dropping out from under the man, and so he doesn't press down on the scale as much. Therefore, the scale doesn't read as high a number. So that's it for this chapter and these units. Hopefully these help.